Hi, this is notes on potential energy or enthalpy diagrams. Um, so our learning targets are we're going to be looking at endo and exothermic reactions. Those could be chemical change, chemical reactions or physical change. And we're going to also be looking at enthalpy diagrams. So enthalpy of a reaction is also known as the heat of the reaction. It's the amount of energy. So we're talking about kilojoules, joules, calories, kilocalories, absorbed or released during a chemical reaction. And it's the symbol is delta, change in enthalpy, H. So remember, it says chemical reaction here, but this can also be used for anything physical change, like a phase change too. Not sure if you remember this reaction where we burned magnesium in the fume hood when we were at school. So I wanted to use this reaction to show you what a thermochemical equation is. So it's just a normal chemical equation, and you do want to have the states of matter in there because it's important, and the amount of energy can change sometimes depending on the state of matter. But what I want to show you is we know that reaction was very exothermic. The energy, as the magnesium ribbon was reacting with oxygen in the air, there was a tremendous amount of energy being given off into the surroundings. We saw that as light. It was definitely, I'm sure, very hot also. So in fact, the amount of energy that was given off when 2 moles of magnesium oxide are formed is about 1200 kilojoules. So one thing I wanted to show you is a thermochemical equation is just a balanced chemical equation with that energy. And it could be on the right side, which means it's an exothermic process. And it can also be on the left side with the reactants, meaning then that much energy would have to be absorbed or brought into the reaction for it to occur. And then it would be an endothermic process. So now I want to show you what an enthalpy diagram is. This is a graphic way of representing how the reactions enthalpy, they're also that you can think of that as the potential energy is changing over the course of a reaction. So it's a lot of times not very the diagram itself doesn't really have much numbers. It's really a rough sketch. The x-axis is going to be, as time or as the reaction progresses, and then the y-axis is enthalpy. So if we go back to this magnesium synthesis reaction, what we do is the first horizontal line is representing the reactants. So in this case, the magnesium and the oxygen have more potential energy or higher enthalpy than the magnesium oxide. So this is placed down here. Notice I don't have any numbers on the side. I mean, I could have some numbers. I could say that this is 200 kilojoules and maybe this is 1400 kilojoules, because the difference, as magnesium and oxygen become magnesium oxide, there's a lowering of energy. So all of that energy is being given off to the surroundings, which is what we know happens for exothermic. So because there's a drop in energy and we're landing down here with less, we are going to use a negative. So when we pull out the enthalpy of the reaction and it's not in the equation, the thermochemical equation, and it's exothermic, we will be using a negative sign. I want to give you an example of an endothermic process. So this is just regular old ice, solid water melting, and we know from our thermodynamic data that there are 6 kilojoules of energy required to melt 1 mole of solid ice to liquid water. So the energy is going to go into the ice. So this is an endothermic process. So notice that I put the 6 kilojoules now on the reactant side because that energy has to go in here for it to become water liquid. So now if I were to draw a enthalpy diagram, I want to again start with my reactant. My starting substance is solid ice. And then I'm going to end over here with liquid water having more energy, more enthalpy. So now notice the positive. So when you see the delta H, or the heat of the reaction, as standing alone and having just equals and then the value, it's the positive. It's what tells someone that we're talking about the endothermic process. If we were taking and reverse that, let's say we want to go, let me see. So let's say we're reversing this now. So we're taking liquid water and we're freezing it. Now the 6 kilojoules of energy is going to be released. So as the liquid becomes solid, that energy is getting given off into the surroundings. So we show it on the right side of the equation. And if we were to draw this, it's an exothermic process. So our water liquid is going to be higher in enthalpy than our water solid. And our delta H would be -6 here. So in summary, if we want to kind of compare and contrast endo and exothermic processes, we know endo, the energy is going from the surroundings into the system. Exo, it's going from the system out to the surroundings. So if I write the reaction and it's endothermic, I'm going to have that energy on the reactant side. And if it's exo, my energy is going to be written positively for both, because it really just means and on the product side. So if I draw an enthalpy diagram for each, and this is just time. So for this reaction, A and B are going to be lower in enthalpy than C and D. Our delta H here would be positive, whatever that value would be. And then over here, A and B start with more energy, and then C and D have less. Delta H would be negative, whatever this value is. And that energy value, most of the time it'll be kilojoule for what we're doing, but it could be joules, could be calories, kilocalories. So I hope that helps you guys understand enthalpy diagrams.